My name is James McNellis. I am a member of the game engine group at Roblox, where I work on software security. And this afternoon, I know it's the last talk of the conference, and so I know that you're all looking forward to hearing something deeply insightful, something new. So this afternoon, I'm looking forward to talking about something I don't think anybody is talking about. Brace yourselves. Do you know that C++ is unsafe? Oh, all right. Okay, I guess everyone did know that. So yeah, everyone is talking about this nowadays, and actually I think that's terrific. I think over half of the talks I attended at this conference were about C++ being unsafe. So I regret to inform you, I too am going to be talking about how C++ is unsafe. This afternoon I'm going to share a little introduction to control flow integrity, looking a little bit at the history of control flow integrity technologies and how they have been developed and improved over time. I'm going to focus today on what I would call normal-sized computers. So I know there's a lot of people working on like embedded systems and supercomputing, but I'm going to be focusing on like those normal-sized things. So think cell phones up to big servers, looking at major OSs for 64-bit, x86, ARM, and 64. Many of these technologies, though, are like applicable to other target platforms. I'm just not an expert in those spaces. So we will define what control flow integrity is as we go along, but first let's just jump right in and write some code. So this is going to be an interactive exercise just to make sure you're all still awake here at the end of the conference. I'm going to write a little C program. Now I know this is meeting C++, not meeting C, but bear with me. I would like you please to raise one finger when you spot a bug. Excuse me, but not that finger. This is a family-friendly conference. Okay. So I'd like my program to read some input from the user. So first we'll include the std.io header. Then I hear it's good for programs to have a main function, so I'm going to give it a main function. And so far, this is pretty good. I don't see anyone raising anything yet. I'll need somewhere to store the data that the user types in. So I'll add a buffer where I can store the text. And I know that it's a bad idea to leave variables uninitialized. So I'll definitely make sure to initialize the buffer. Great, so now I'm ready to go, and I can call this handy gets function to read whatever the user types in. Oh, I see fingers going up. Yeah. Okay. So yeah, that last line of code has a little problem. As it appears, some of you know, the gets function reads a line of text from standard input into this character buffer. Strangely, tragically, this function does not seem to care how big the buffer is. It only asks us to pass the address of the buffer, not its size. So it'll just keep writing characters into this buffer as long as the user keeps typing. Now, as long as the user doesn't type too much, we're fine. But if the user types like a really long line of text, in this case over 511 characters, then we may be in some trouble. Gets will keep writing right past the end of the buffer, obliviously overwriting whatever might be there in memory. We can't really blame gets for this, though. This is what it's documented to do. Maybe we could blame the user, though? Like maybe we could just put it in our program's documentation, like, hey user, don't type really long lines of text. Maybe, but like I don't like blaming the user, and even when like the user does something wrong, it's much better if we handle this error gracefully and let them know that something has gone wrong. Much more importantly though, when we read from standard input, it may not be from the user typing text into their local console. Standard input may be coming from a file, or perhaps even from an untrusted user over the network. And that, in fact, is how this code is used, or I should say was used. This is actually real code from a real program, or it's close to the real code. The real source code dates back to the 1980s, so in reality, it looked like this. C looked a little differently back then. Anyway, this code comes from the 4.3 BSD sources for the finger daemon. That's why I asked you to raise one finger if you saw something wrong. Yeah, very, very funny. So Finger was this tool that would let you connect to a remote computer and query it for information about a user. It was commonly on like Unix systems. So when the Finger daemon, which handled these remote requests, had this call to gets in it, as long as the remote user was a polite, good person and used Finger correctly as it was intended to be used, then there was no problem. But if a rude user connected and sent more than 511 characters to the server, then that could cause the buffer to be overrun, which could result in other memory being corrupted, which could lead to untold mayhem. And I'm sure you're all surprised. That's exactly what happened. Otherwise, we wouldn't be looking at this code. In 1988, this code formed a critical part of the exploit chain used by the Morris worm, which was one of the first successful worms to spread over the early internet. So this is a classic memory safety bug. And worse, it's a remotely exploitable memory safety bug. With this memory safety bug, a remote attacker is able to cause the program to overrun this buffer and overwrite anything that follows it on the stack. And as we know, there are some very important things on the stack. If we look at the stack when this program is running, we'll find something like this. The stack grows downward, so at the top we find the data for the function that is called our main function, the start function perhaps. And then we'll have the return address for the main function. And then we'll have the line buffer, which I've shrunk down to 16 bytes so it would fit on the slide without having really long slides. So as long as our user is polite and brief, we don't have a problem. But imagine our user sends a very long string of A's. A is the traditional character for this sort of thing. So first, the gets function will fill the line buffer on the stack. 41 is the ASCII code for the letter A. And then there's still more data, and gets doesn't know that it's filled the buffer, so it just keeps writing, corrupting the return address. So now, instead of our real return address, we have this value 41 repeated. The state of our program is hopelessly broken now, but it's likely to keep running just fine until main tries to return. When main tries to return, it'll pop that corrupted return address off of the stack, and it'll try to transfer control to this address 41 repeated. That's probably not a valid address, so the CPU will raise an exception, not a C++ exception, but a hardware exception, and this will generally result in our program being terminated. The key point here is that by corrupting the return address, an attacker can mess with the control flow of our program. If an attacker corrupts the return address with a nonsense value, like 41 repeated, then they can cause our program to crash. That's bad. Crashing is bad. I don't like it when my programs crash. But actually, crashing is actually the least bad thing that can happen here. By overwriting the return address with an invalid pointer value, the attacker can make our program crash. But if the attacker overwrites the return address with a valid pointer value that points to actual memory where actual executable code exists, then they can redirect our program to start executing code other than the code that it's supposed to be executing. The attacker can effectively hijack execution of our program and make it do whatever they want. So where might the attacker want to redirect control flow to? Well, the most straightforward method of attack is just for the attacker to bring their own code with them and force our program to start executing it. So we can already see here that the attacker can copy arbitrary bytes into our program. So if the attacker wants, they can take their own program, compile it or assemble it to machine code, and then send that as part of the string that they're going to send to our program. So I've shown that here. They've just appended it into the data that they're sending. And then the attacker can set that area where the return address is with a pointer to where their program is located on the stack. Now when main returns, it won't cause our program to crash. It'll cause our program to start executing the attacker's code, which is not so great. So this sort of vulnerability is called an arbitrary code execution vulnerability because it allows an attacker to hijack control flow and execute arbitrary code inside of our process. When this sort of vulnerability exists in a program that's accessible over a network or across privileged domains, it's also called a remote code execution vulnerability because it allows an attacker the ability to execute arbitrary code remotely inside of our process. Arbitrary code execution vulnerabilities are among the most severe, most catastrophic classes of software vulnerabilities because once an attacker achieves arbitrary code execution inside of a process, they can do anything in there. It's as if the attacker got you to run their own program for them in the security context that your program is running in. Great. Not great. So the finger daemon had this exploitable memory safety bug, and when it was exploited, there was extensive damage. And obviously, there's an easy fix for the code here, right? We just need to replace this call to gets with a call to fgets, which takes the size of the buffer. And that fix was in fact made. Actually, I had some trouble finding the original vulnerable source code to share because almost every archive copy online had that patch already applied. So all right, great, we can fix that program. Problem solved. Except it turned out that tons of problems had these sorts of memory safety bugs that an attacker could exploit to overrun a stack buffer and hijack control flow. And in the years that followed, more and more of these attacks were observed, and as time went on, the complexity of the attacks grew as well. The bug in finger D is obvious when we look at the code, but in most cases, the memory safety bug is far more subtle. So some people started asking, would it be possible to develop a systematic defense against attacks that exploit stack buffer overruns? And that's where control flow integrity starts to take form. Control flow integrity technologies do not fix memory safety bugs. That's not to say that we shouldn't fix them, just that fixing them is a separate thing. Rather, with control flow integrity technologies, we accept that our program may have memory safety bugs in it. We accept that we may not be able to find and fix them all. We accept that an attacker may be able to find one of these bugs and exploit it to overrun a stack buffer and corrupt a return address. And so our first rudimentary goal is going to be this. Even if an attacker is able to overrun a buffer on the stack and overwrite the return address, we want to prevent the attacker from successfully hijacking the control flow of our program. In other words, even if this sort of memory safety bug exists, we do not want it to be usable by an attacker to achieve arbitrary code execution. So, let's go. An attacker can overrun a stack buffer, and we can't stop them from corrupting the return address. But maybe we can detect that the return address has been corrupted, potentially by a malicious user, and maybe we can detect this corruption before we execute the ret instruction, and before we potentially transfer control to the attacker's code. So the first systematic defense that was developed here was the stack canaries. Stack canaries were first developed in 1997 in a GCC patch called Stack Guard. The idea was developed further in the following years, and it was gradually adopted by major toolchains in the early 2000s. I think Visual C++ was the first toolchain to have it as an official feature in 2003. Visual C++ calls them security cookies, and they've been enabled there by default since 2005. So if you're building software for Windows, you probably are using stack canaries. With GCC and Clang, you still need to opt in at compile time. The idea of a stack canary is quite simple. Here I have our vulnerable main function with its call to gets. We're going to add a global variable. In this case, I've named it stack check guard, which is the name it has in the GCC runtime library. In the Visual C++ runtime library, it's called security cookie. When our program starts up, we will initialize this global variable with a random number. I say we, but really it's just magically initialized for us by the operating system or the runtime library. By the time our code starts running, the random value is just there. Then at the beginning of our vulnerable main function, we're going to add a local variable named canary and initialize it with the value of this stack check guard global variable. If we look at what the stack looks like, this results in our canary being present on the stack between the return address and our line buffer. With this arrangement of the data, we can see that if an attacker overruns the stack buffer and overwrites the return address, then the attacker will also end up overwriting this canary value on the stack. So at the end of our function, just before we return, we'll go and we'll read the value of the canary from the stack and make sure it has the same value that we wrote there. It should still have the same value as the global variable, and if it doesn't match, then we know that something bad has happened. Now, we don't know whether it has been corrupted accidentally or maliciously, but we do know that it's been corrupted somehow. And so at this point, it's possible that the return address has been corrupted. So at this point, we have to figure out what to do. And it turns out the only sensible option is to terminate the program. Now, terminating our program or causing it to crash is not great, but we have no idea what the state of our program is, right? We know that this memory safety bug has occurred. We have no idea whether it's possible for us to continue executing correctly or even what that would mean. If the return address was corrupted accidentally, then the program was probably going to crash anyway when we return. If the return address was corrupted maliciously, then forcing the program to crash is a whole lot better than executing the attacker's code. And so this is a trade-off we're going to make with most of the technologies that we'll look at this afternoon. We accept that we may have memory safety vulnerabilities in our code, and we just want to blunt the potential impact of those vulnerabilities. So without the stack canary, an attacker can potentially overrun the stack buffer and corrupt the return address and achieve arbitrary code execution. But once we add the stack canary, the attacker can still overrun the buffer, but now can only force the program to crash, which makes it a potential denial of service vulnerability. That's not ideal, but it's a huge improvement over remote code execution. Now, what I've written here on the slide is conceptual. Throughout this talk, I'll be showing a lot of code, and almost all of it is just conceptual. All of this instrumentation code that gets added is added automatically by the compiler, and I'm just showing conceptually what it does. The real-world details may be a little different and may differ across implementations. Again, just trying to keep things at the conceptual level to demonstrate the high-level ideas. So the important thing for this example is you don't have to write any of this in your own code. The global variable is defined and initialized by the runtime library, and the compiler will do all the work to generate the code to place the canary on the stack at the beginning of the function, and then check to make sure it's valid at the end of the function. This is really cool because to get this protection, we don't have to change our code at all. We don't have to go and hunt down and fix every potentially vulnerable stack buffer. We can just enable this compiler feature and recompile our code, and every function is protected. Stack canaries are highly effective because they are simple, their runtime cost is generally very low, and they prevent one of the easiest methods of hijacking control flow. Unfortunately, bad actors are very motivated to break our software, so they didn't just give up, and instead they sort of developed ways to bypass the canary check. The most straightforward attack vector is like if the attacker can just find a way to get the program to give them the canary value. If they can do that, then the attacker can just incorporate the expected value at the right location in the data they're sending so that when the buffer overrun happens, it effectively just overwrites the canary with the same value that it had. There's various kinds of information disclosure vulnerabilities that an attacker could potentially leverage here to exfiltrate that value. There are some enhancements to stack canaries that make them a bit harder to thwart in that way. So for example, in some implementations, a per thread canary value is used. So an attacker would have to pick the right canary. They'd have to know what thread they're going to end up, their code is going to end up running on. It's common across, I think, most implementations now to actually XOR the canary value with the stack pointer so that it has a different value each time it's written in a different location in memory. I will leave it to all of you to go and look into those little details if you're interested. The main limitation of stack canaries is that they only protect against this one form of memory safety vulnerability, stack buffer overruns. If an attacker can find a different kind of memory safety vulnerability that allows them to overwrite the return address without perturbing the canary at all, then the canary won't do anything to stop them. So those are stack canaries. While there are ways to bypass the canary check, and while now, a couple of decades later, there exist more sophisticated exploitation techniques that stack canaries can't defend against, this doesn't mean that they're not a useful security feature. To the contrary, they prevent one of the easiest to execute, most straightforward forms of attacks, which means that attackers now have to use more complex attacks. This makes attackers' jobs harder, and it makes development of reliable exploits more expensive. And that just by itself is a win. Stack canaries, as I said, are also inexpensive at runtime, so the cost of this protection in runtime overhead is very low, which is also a win. Stack canaries were one of the first technologies to become widely adopted here. There were two others that were developed and deployed in the early 2000s, and we'll look at those. One is a software technology, and one's a hardware technology. In our stack buffer overrun example, I sort of brushed over the one tiny important detail. Our attacker copies their code onto our stack, and then they set the return address to point to it. How do they know where that is? After all, even in a 32-bit process, let alone a 64-bit process, the address space is quite big, and the stack is quite small. And the simple answer is, at the time, the operating system just always allocated the stack at the same address. Actually, the operating system generally preferred to allocate everything at the same address each time a program was run. It'd load the program itself at a consistent address, and it'd do its best to load shared libraries at consistent addresses and the stacks, and even within the heap, allocations would often follow very consistent patterns. Why? Well, because that's the easiest thing to do, and it's the fastest thing to do, and computers have not always been as fast as they are today. So while it's the easiest thing for the OS to do, it also makes things a lot easier for attackers, right? Because now they know with a high certainty how things will be laid out in memory in the process they're targeting. It's like they have a map of where everything's going to be. So to make things harder for attackers to find things in a running process, operating systems started implementing address space layout randomization, or ASLR, which is exactly what its name implies. Instead of allocating binaries and stacks and heaps and other things at fixed or relatively predictable locations at runtime, the OS will randomize where it allocates them. Most major OSs added support for ASLR in the early 2000s, like the first decade after the millennium, around the same time that stack canaries started to gain widespread use. When ASLR is used, if an attacker wants to execute a successful remote code execution attack, they'll generally have to find a way to get the program to give them some information about how things are laid out in memory. Sometimes there's weaknesses or limitations in the ASLR implementation that may allow them to discover this information, Or sometimes they may rely on some information disclosure bug where a program might leak some pointer address inside of a log. So ASLR does not completely solve any problem, but at a minimum, it adds extra hurdles that an attacker is going to have to clear in order to achieve a successful exploit. Yes, so I've said all of that. All right, next up. In our stack buffer overrun example that we've been looking at, the attacker takes their own code that they want to execute, they copy it into our process, onto our thread stack, and then they get our program to execute it. So what if the CPU just didn't let you do that? The x86 family of CPUs has supported marking regions of memory as non-writable or read-only since virtual memory support was first added in the 286 in 1982. So that's been around since before I've been around. If you mark a region of memory as non-writable, and then your program tries to write to it, the CPU will raise an exception, and that'll generally result in your program terminating. It'd be nice if we could also mark a region of memory as being non-executable. So then when the OS would go and allocate a stack for a thread, it can tell the CPU, oh, this region of memory where the stack is should never contain executable code, and so we should never try to execute code from it. With non-executable memory, if a program tries to return to, or call to, or jump to, or transfer control in any way to an address that points into a non-executable region of memory, the CPU won't let that control transfer take place. It'll raise an exception, and this exception will generally result in our program terminating. Non-executable memory was not a new idea, it was just a relatively late addition to x86. And x86 CPUs only started supporting this in 2003, 2004. There's a lot of different names for this feature, but they all effectively denote the same things. AMD calls it NX for no execute, Intel calls it XD for execute disable, ARM calls it XN for execute never, and then Microsoft has data execution prevention. There's probably various other names as well, but they all mean the same thing. The way I describe this feature, it might sound like we're going to mark some regions of memory, like the stack, as non-executable, but in practice, it's much more like the reverse. The default will generally be that we allocate most memory as non-executable, and then in the few places where we actually load executable code into our program, we'll mark that memory as executable. For the most part, this will only be parts of our binaries that get mapped into memory, plus maybe some JITted code at runtime. So now, if we come back to our example program, an attacker may still be able to exploit the stack buffer overrun. They may be able to bypass the stack canary somehow. They may be able to copy their code onto the stack. They may be able to bypass ASLR and figure out the address at which their code is going to be located. They may be able to overwrite the return address with that address. But now when the CPU goes to execute the ret instruction and tries to start executing the attacker's code on the stack, it'll see that region is marked as non-executable, and so instead of executing the attacker's code, it'll raise an exception that'll generally cause the program to be terminated. So, success, problem solved. I hope you enjoyed the talk. If this talk was given, I guess, in 2008, that would be the end, actually. So that's, So maybe not. Okay, so non-executable memory was a huge security improvement, and when combined with stack canaries and ASLR, these three technologies together made it much, much harder to successfully hijack control flow. But as we noted previously, bad actors are highly motivated to break the programs that they are attacking. So as these increasingly advanced defensive technologies were gradually adopted, attackers became increasingly sophisticated in their attack methods. So now that we can mark memory as being non-executable, an attacker can't bring their own code into our process for us to execute. That's great. Unfortunately, our process is already full of code. It sort of has to be, because if it wasn't, you wouldn't be able to do very much. Notably, we probably have a bunch of shared libraries loaded. We probably have the C runtime library loaded. And that C runtime has all sorts of very useful, very generic functions, like the system function. The system function lets our program run some other program. This seems like a very useful thing to have in a runtime library, but it also sounds like the sort of thing an attacker might find useful so they can get our program to run something else in the same privilege domain. So what attackers started doing is, instead of bringing their own code with them, they started using code that was already available in the process and which was already marked as executable. The most basic form of attack here is called return to libc. So with a return to libc attack, the attacker will overwrite the return address with the address of some function inside of libc or some other library or from the program itself. This way, when the function returns, instead of returning to its caller, it'll end up jumping to the start of that library function, like the system function, almost as if that function had been called. Okay, so the attacker can hijack control flow and get our program to call the system function for them, and that's bad. But the system function requires a parameter, and if the attacker wants to do something useful with this, they're going to need to figure out how to set that parameter value to a value that's useful to them. On 32-bit x86, this is generally really easy because in most calling conventions, arguments get passed on the stack. We've already seen the attacker can put whatever they want on the stack, maybe, and so the attacker just needs to copy their command string somewhere and put the pointer to that string in the right location on the stack so that when they return to the system function, it'll find it in the right place. However, on 64-bit x86 and many other architectures, in the predominant calling conventions, the first few arguments get passed in registers. For example, when calling the system function on 64-bit x86 Linux, the address of the command string must be placed in the RDI register. Thankfully, while it's possible to exploit memory safety bugs to overwrite memory, registers aren't memory, so you can't take the address of a register or overrun a buffer and overwrite the value in a register. So even if our attacker can overwrite arbitrary memory, they can't overwrite register values, unless they can. So with a return to libc attack, the attacker overwrites the return address with the address of a function that already exists in our program. Our attacker, however, is not limited to functions. Our attacker can overwrite the return address with the address of any instruction, even if it's in the middle of a function. And on x86, where there's variable length instructions, they could even write it to in the middle of an instruction and start decoding from instructions that don't even exist in our program. So as an example, if somewhere in our program we have the instruction sequence pop RDI ret, then the attacker could overwrite the return address with the address of this pop RDI instruction, and then put their value of choice just above it on the stack. And when the function returns, it'll transfer control to this pop instruction, which will load the attacker's value into the RDI register, and then it'll execute a ret instruction. And the attacker can just make sure to carefully construct the stack so that that ret will return to the start of the system function. By chaining these two operations together, the attacker can load the address of their command string into the right register and then call the system function to execute that command. Little instruction sequences like this have been dubbed gadgets, and an attack involving chaining these gadgets together has been rather cheekily called return-oriented programming, or ROP. Most unfortunately for us, a lot of research has been done here, and it turns out that most programs contain enough gadgets that return-oriented programming is Turing complete. So an attacker can generally transform any program into a chain of gadgets, and this unfortunately means that an attacker can achieve arbitrary code execution within our process, even without being able to execute any code of their own. All right, so we set out at the beginning of this talk with a goal. Even if an attacker can overrun a buffer on the stack, we want to prevent that attacker from being able to hijack control flow. Stack canaries, address space layout randomization, and non-executable memory all make it harder for an attacker to hijack control flow by overrunning a stack buffer. But these are all speed bumps of a sort, and as we saw, there's ways to bypass them. As attacks get more sophisticated, we also need to become more sophisticated with our defenses. And over the last decade, there's been two major new technologies that have been introduced that bring substantially stronger defenses. However, before we look at those, I'd like to refine our threat model so that we understand and account for the full breadth of possible attacks. So far, we've been looking at the case where an attacker overruns a buffer on the stack. This, of course, is a memory safety bug, but it's not the only kind of memory safety bug. Memory safety bugs come in all sorts of fun flavors. Some are a little bad, and others are catastrophically bad. The worst memory safety bugs are those that allow an attacker to perform arbitrary reads or writes of data in our process's address space. With an arbitrary read vulnerability, an attacker can read the value of any byte in our process's address space. And with an arbitrary write vulnerability, an attacker can write any value of their choosing to any location in the address space of our process. Now, when we first described that, both of these might seem extremely unlikely, but in fact, they're more common than we might think. Here, for example, I've got a very simple class. This is, I think, one of only 2 slides with C++ code in it. It has a std vector as a data member, so std vector is good. That's going to help us stop, having memory safety bugs. And it has this member function that lets a caller update the value at a particular index. Now, there's nothing wrong with this function. This is perfectly fine. We have this all over the place in our code. But if there's any code path through the program where the index and the value are controllable in some way by the user, like some network packet we're parsing or some user input or some file that we're reading, and we don't do proper sanitization, then this function can potentially become part of an arbitrary write vulnerability. With a carefully calculated out-of-range index, an attacker can cause this function to write their value to any location in memory. So going forward, we're going to consider a broadened threat model. Even if an attacker can exploit arbitrary read and write vulnerabilities and alter the return address, we want to prevent the attacker from successfully hijacking control flow. That is, even if an attacker has the worst possible memory safety bugs at their disposal, we want to prevent the attacker from being able to tamper with control flow as it exists in the program. Even if an attacker can change any value in memory, we don't want them to be able to hijack control flow. By assuming that the attacker has the worst possible vulnerabilities at their disposal, we ensure that the defensive techniques that we develop will be robust regardless of how severe the actual memory safety vulnerabilities in our program are. I've added one caveat here, which is that we assume the attacker cannot change memory protections. So an attacker can't make a non-writable page of memory writable or make a non-executable page of memory executable. This is a fairly reasonable caveat because to change memory permissions, a program has to make a syscall, for example, calling mprotect or virtual protect, and code that makes these syscalls is relatively rare, and it's rare enough that it's actually somewhat tractable for us to go and audit the code that does that and make sure we're using those functions in a safe way so that an attacker can't achieve changing page permissions. So that's our goal. It's ambitious. Let's see how close we can get to it. So if we want an even stronger defense against control flow hijacking, perhaps it's time to reconsider some fundamental parts of our computer architecture. So let's rethink the stack. If we look at the thread stack, it looks something like this. We have A's return address, the address that A will return to control to when it's finished. Then we have A's local state. Then A calls B, and we have B's return address and its local state, and so on. So we have one stack, but we use it to store two completely different kinds of data. We use it to store our control flow state, that is our return addresses, and we use it to store our function local states, our local variables and temporaries and other such things. This picture seems natural to us because, of course, this is how things have always been done, effectively since the beginning of structured programming. It's easy to understand why in an era when computer memories are measured in bytes and kilobytes, it made sense to combine these things. But we don't have to store these things on the same stack. What if we split this data up and we've got two stacks for each thread? We'll have one stack which contains only our control flow state, that is our return addresses, and we'll have a different stack somewhere else in memory that'll contain our function local state. If we do this, we can see that obviously a stack buffer overrun could never result in a return address being overwritten. The stack buffer would be over here, or on the local variable stack, but the return address would be over there on the control flow stack in some completely unrelated region of memory. So that's pretty cool. But there's actually a second, less obvious benefit of doing this. Local variables need to be generally accessible. What I mean is local variables are, from our perspective as C++ programmers, just C++ objects. We need to be able to read from them and write to them and take their addresses like we do with any other C++ objects. But the same is not true for return addresses. There's only two instructions that should be touching return addresses, call and ret. And we can put a little asterisk on that because there's exceptions, like exceptions. But those exceptions are truly exceptions, and maybe we can deal with those as special cases. That's a very tiny amount of code. So if we split our stack in two and store our control flow state separately from our normal program data, maybe we can make it so that only call and ret instructions can touch that control flow stack. Just like we added the ability to mark memory regions as non-executable, maybe we can add the ability to mark a memory region as only touchable by call and ret instructions. If we can do that, then we can make it completely impossible for an attacker to hijack control flow by overwriting a return address via any memory safety bug at all, because we would make it impossible to overwrite the return address on this control flow stack. So, in 2020, Intel introduced a new set of features to the x86 architecture, which they called Control Flow Enforcement Technology, or CET. One of the features added by CET is called the shadow stack, which gives us something kind of like this split stacks approach. When we enable shadow stacks, each thread has its normal thread stack, that contains both return addresses and function local state. So it's exactly the same as the thread stack before. There's no changes to that. However, each thread also now has a second stack called the shadow stack, which contains only the return addresses. The call instruction is updated so that it now pushes the return address onto both the thread stack and the shadow stack. Then the ret instruction pops the return address off of both stacks. It compares the values, and if they're not the same, or if they are the same, then the return is executed. If they're not the same, then something has gone wrong. The return address on the thread stack has been corrupted somehow. And so in this case, the CPU will raise an exception which will terminate the program. So the shadow stack is specially protected, and it's not generally accessible. So only call and ret instructions can access it, and then there's a few other general special purpose instructions for implementing things like exception handling and stack unwinding. And that's basically it. Shadow stacks are surprisingly simple. The first reaction we might have is, this seems more complicated than it needs to be. Why not just go with the split stacks approach? Like, that certainly seems much cleaner. And the answer is probably unsurprisingly compatibility. The behavior of the call instruction where it pushes the return address onto the thread stack has been part of x86 since the very beginning. And most notably, major software ABIs, including the Windows ABI and the System 5 ABI, depend on this behavior. And basically, all software in existence would be broken if that was changed. So while this approach is not as architecturally clean as having two completely separate stacks, it maintains legacy compatibility and is just as effective from a security perspective. So shadow stacks completely prevent control flow hijacking via malicious modification of the return address. With them, we completely achieve the goal that we set out for ourselves, so that's super awesome. Intel and AMD have both supported shadow stacks in their hardware that's been released since 2020, so 5 years now. Windows has supported shadow stacks since the hardware was available. Linux support came a fair bit later, but it is there. So that's shadow stacks. Shadow stacks are the gold standard here. They're a super awesome advancement in security on x86. But what about ARM? So ARM has also introduced a new technology for protecting return addresses, but their technology is completely different. So let's take a look at pointer authentication, or PAC. The first thing we have to note is that the call and ret instructions work differently on ARM than on x86. On x86, the call instruction pushes the return address onto the stack and then transfers control to the call target. Then the ret instruction pops the return address back off of the stack and transfers control there. On ARM, well, first off, there's no call instruction. ARM has this BL instruction, which stands for branch with link, and it's used for direct calls, and then there's a BLR instruction, which is used for indirect calls. Whereas on x86, the call instruction pushes the return address onto the stack. The ARM BL instruction places the return address into a register, and specifically it's register X30, or LR. It's called the link register. And then it transfers control to the call target. Then, since the call instruction doesn't push the return address onto the stack, the ret instruction doesn't pop it off of the stack either. Instead, it takes a register as its operand and transfers control to the address in that register. Most of the time, we'll specify the link register as the operand because that's just how it's done. And in the assembly language, like, the link register is the default if you don't explicitly specify a register. So this design has a really neat feature. Here on the left, I have a main function. It doesn't do anything. It just returns 0 to its caller. So hopefully there's no memory safety bugs in there. Here on the right, I have the code the compiler will generate for this function. Even if you don't know anything about ARM, it should be pretty easy to understand. First, we move the value from WZR, which is the 0 register, into W0, which is where the return value goes. So that's setting our return value to 0. Then we execute a ret, and we pass it X30, which is the link register, which is where our caller put the return address. See, now you're all ARM assembly experts. You can go and put that on your LinkedIn profile and look really impressive. As an aside, you may also note there's a bunch of white space, which should tell you we're going to fill this in with more code as we go along. So when main is called, its caller puts the return address in the link register X30, and then it transfers control to main. Inside of main, we do what we need to do, and then when we go to return, we tell the CPU, return to our caller, and you can find the return address in the link register. Note that at no point in time was the return address written to the stack. And in fact, on ARM, as long as a function doesn't call any other functions, it never has to write its return address onto the stack. It can just leave it in the link register. This is really convenient. It reduces otherwise unnecessary memory operations, which is kind of cool. But now we have a problem. If our function calls another function, for example, here I've added a call to f inside of main, you can see that the compiler has added a BL instruction, which is the ARM call instruction. Now, when main is called, its return address gets put in the link register and it starts executing. It then calls f, and that BL puts f's return address into the link register, and now we've lost main's return address. So if we have a function that calls other functions, which is called a nested function, we have to save the return address ourselves, and generally that means we're going to have to put it on the stack. So in addition to the BL instruction to call f, the compiler is going to add two other instructions to our function. In the prologue, at the very beginning of our function, the compiler is going to take the return address in the link register, x30, and push it onto the stack. That's what this str instruction does. Don't worry about all the wild punctuation. It's a surprisingly complicated instruction, but the details don't matter for us. All that matters for us is this pushes the return address onto the stack. Then in the epilogue, at the end of the function, just before we return, we pop the return address back off of the stack into the link register, x30, and then we execute our return through it. The important thing to note is that on x86, pushing and popping the return address on the stack is automatic and implicit in the way the call and ret instructions work. On ARM, it's explicit. If a function needs to save its return address, it's got to do it itself. Shadow stacks made sense on x86, where the call instruction was already pushing return addresses onto the stack. Like, why not push it onto two stacks? But on ARM, it's not so obvious that that idea fits in with the fundamental design for the architecture. It's not clear that it makes sense to change the behavior of the BL and ret instructions. And we can't reasonably change these str and LDR instructions because they're just general purpose load and store instructions. There's nothing in the instruction that says, this is a return address that I'm pushing onto the stack. We have a unique opportunity on ARM, though. Because our function explicitly writes its return address onto the stack, it has the option of doing something with that return address before it writes it to memory. So what to do? Let's take a step back. Imagine we have some data, any data, maybe it's an email or a network packet or a file or an image, and we want to ensure that if that data is tampered with in some way, we'll be able to tell. We would sign it, like cryptographically sign it, right? So that's what ARM did with pointers. ARM pointer authentication was added in ARM v8.3, which was published in 2016 or 2017. Apple's A12 CPU was the first hardware to include it in 2018. Pointer authentication provides hardware support for cryptographically signing pointers and then cryptographically authenticating those signatures. Pointer authentication is also called PAC, P-A-C, as the signature that it produces is called a pointer authentication code. So what we're going to do is at the beginning of our function, before we write the return address onto the stack, we'll add this PAC instruction, and it will cryptographically sign the pointer in the link register. Then, at the end of the function, after we read the return address back off of the stack, but before we transfer control through it, we'll add this auth instruction, auth for authenticate, and it will recompute the signature for the pointer in the link register. If the signature does not match, then we know that the pointer was tampered with or corrupted. An exception can be raised here and the program can be terminated. Okay, so the first question we're going to have to solve is, where are we going to store this signature? And to answer that, I would like to ask you, the audience, a question. If we are running on a 64-bit CPU with a 64-bit OS, and our program is a 64-bit program and it has 64-bit pointers, how big is our address space? Just shout it out. Oh, there's a lot of numbers, but nobody said 64. That's good. Yeah, it depends. For our purposes here for the moment, let's say 48 bits. We only have a 48-bit address space. So we have a 64-bit pointer, and we only use 48 bits to store the address, which means we have 16 unused bits. Actually, not quite, because on ARM, bit 55 has this special meaning, but okay, that's fine. We have 15 unused bits. So let's put the signature there. So our pointer will have 48 bits, this special bit 55, and a 15-bit signature called a pointer authentication code, or PAC. So the way this will work as follows. We have our pointer, which for our use case here is our return address, and we feed it into this PAC instruction. The PAC instruction also takes two other operands. So first, it's got to take the key that's going to be used for signing. Now, we don't want there to be any possibility for the attacker to read this key, right? Because then they could sign their own pointers. So our program doesn't actually have the key. The kernel will generate a key for our program, and it'll place it in a special CPU register that our program can't access directly. Our program will just refer to this key by an identifier. On ARM, the CPU supports up to 4 keys, like there's 2 for signing instruction pointers and 2 for signing data pointers, and in different implementations, they get different uses. So we just say which of those keys we want to use. Then the pack instruction can also take a 64-bit modifier value, which can be any value we like. So it takes these 3 inputs into the pack instruction, and it uses a cryptographic algorithm implemented in hardware, so it's very fast, and it produces a signature for our pointer. It stores that signature in the unused bits of our pointer, so I've shown that here in green, and we get a signed pointer. We can then safely take our signed pointer and write it to memory. At the end of our function, we'll read that signed pointer back from memory, and at this point, we need to authenticate the signature to make sure that it's valid. To do this, we use an auth instruction, and like the pack instruction, it takes 3 inputs. We give it the signed pointer, and then we have to give it the same key and modifier value that we used when we signed it. The auth instruction will basically take the pointer value that's still inside of that, and it'll recompute the signature. And if it matches the signature that's stored in the pointer, then the auth instruction will remove the signature from the pointer, leaving us with the original pointer value. We'll then pass that pointer to the ret instruction, and we'll transfer control, and everything works as it's supposed to. If the signature is invalid, it might be nice if the auth instruction would raise an exception, but for reasons, it doesn't. Instead, what it does is it sets the high-order bits of our pointer to an invalid state. So basically, it makes sure they're not all 0. This way, when we attempt to dereference or transfer control through it, an exception will occur then, because the CPU is going to be like, well, this pointer is invalid. So the auth instruction won't raise an exception, but the ret instruction that follows it will. So if we come back to our example function, we can fill in the last details. At the beginning of our function, we'll use pack IB. This will sign the return address in X30 using the IB key, and then we pass the stack pointer as the modifier value. We could use 0 or a constant modifier. If we did so, though, then when we go to sign a pointer, it'll always have the same signature, regardless where we're writing it in memory. By using the stack pointer as an input to the signing algorithm, we ensure that we get a different signature when a return address is written to different places in memory, and that just makes it a little harder for, if an attacker is able to exfiltrate these, to be able to reuse them. We pick the stack pointer for this purpose because it's the same, both at the beginning of the function and the end, or it had better be the same. So then at the end of our function, after we load the signed return address back from the stack, we'll use the auth IB instruction, which authenticates the return address in X30, again using the IB key and the stack pointer as our modifier value. If authentication succeeds, now X30 will contain the original link address, or original return address, and our ret will transfer control to it. If authentication fails, then X30 will contain a tainted pointer value, and when our ret attempts to transfer control, it'll raise an exception. There's one final implementation detail here to note, I suppose. Obviously, one disadvantage of pointer authentication is that our compiler has to add these instructions to the beginning and end of all of our non-leaf functions, which means we're going to have to recompile our program. And because these are new instructions, if we do this, then our program won't run on older CPUs that don't understand the new instructions. Those CPUs will raise an illegal instruction exception, which, good news, means our memory safety bugs won't be exploitable, but also our program won't run. So in order to make pointer authentication partially backward compatible, ARM included several special purpose instructions that can be used just for signing and authenticating return addresses. So there's this pack IBSP instruction, which means the exact same thing as what we had before, and similarly the auth IBSP instruction. And these special purpose instructions are encoded in such a way that older CPUs will just treat them as no ops and ignore them. So the compiler can choose either of these instructions. So that then is pointer authentication in a nutshell. At this point, pointer authentication is available on most relatively recent 64-bit ARM devices. Major OSs support it, including Linux, Android, iOS, Mac OS. I could not find any information online about the current state of affairs on Windows for ARM. So we can compare and contrast the protection offered by shadow stacks and pointer authentication. For shadow stacks, it's easy. An attacker cannot successfully hijack control flow by corrupting any return address because an attacker can't write to the shadow stack. That's great protection. Pointer authentication also offers great protection, but it's not quite as great. With pointer authentication, an attacker can modify a return address in memory as long as they substitute that return address with an address that's properly signed. With stack canaries, we discussed how an attacker might be able to leverage some sort of read vulnerability to exfiltrate the canary value. Similarly, with pointer authentication, an attacker could leverage a read vulnerability to exfiltrate a signed return address. But crucially, an attacker is limited to real return addresses that our program has already signed and written to the stack somewhere at some point. So in general, return-oriented programming is not possible, and attacks here would be very narrowly constrained. One of the other weaknesses of pointer authentication is that an attacker can just try to guess the signature. Now, when we have a 15-bit pack, an attacker has about a 1 in 32,000 chance of guessing the right signature value, and those are not good odds. But unfortunately, pointer authentication is not the only thing that these higher-order bits may be used for. Notably, ARM also supports memory tagging, which reserves the higher-order 8 bits to store a memory tag. And now ARM also supports larger address spaces up to 52 bits instead of 48. And actually, when I was doing research for this talk, I learned that ARM v9.4 increases that maximum to 56 bits. And if you're looking at this diagram and trying to figure out how everything fits together, I cannot tell you. Anyway, if you enable memory tagging and you use the enlarged 52-bit address space, that leaves you with 3 bits to store the pack. And if we know our powers of 2, that means that it gives an attacker a 1 in 8 chance of guessing the right signature. And those are potentially more palatable odds. Now, this is the worst case. Like, enlarged address spaces are not in widespread use, and even like on mobile devices, often like smaller address spaces are used. But even if we ignore this worst case, shadow stacks are clearly better from a protection perspective. So wouldn't it be nice if ARM would add support for them? Well, good news. ARM v9.4 announced in 2022 also adds a new feature called the guarded control stack, and guarded control stacks work more or less the same way as Intel's shadow stacks. So I'm not going to talk about them because I'd basically just be repeating myself. To the best of my knowledge, there are no ARM v9.4 CPUs in production yet, but someday in the not-too-distant future, we can look forward to guarded control stacks being available, and then we'll have shadow stacks everywhere, which will be awesome, and we'll have completely solved the problem. Or we'll have completely solved the first half of the problem. Because there is, unfortunately, another half of the problem. For every return that we execute, there must have been a corresponding call. And so I am extremely excited right now because we get to spend the rest of our time together talking about my favorite thing and my least favorite thing, function pointers. So if we look at the execution of the functions in our program, we can represent the call graph as, well, a graph. In this call graph, each function is a node, and then between these nodes, we have directed edges. When one function calls another, this forms a forward edge in the graph, and when a function returns to its caller, this forms a backward edge in the graph. So in short, a call instruction or a BL instruction on ARM forms a forward edge, and a ret instruction forms a backward edge. Stack canaries, shadow stacks, and return address signing all protect against attempts to hijack control flow by corrupting return addresses. So all of these control flow integrity technologies provide what is called backward edge control flow integrity. What about the forward edges of the control flow graph? Can calls be similarly attacked? And if so, should we be developing technologies to defend against those attacks? Every return is the same. Each function has the return address of its caller stored somewhere, either on the stack or on ARM in the link register. The target of a return instruction is always dynamic, right? It depends not on the function that we're currently in, but on what function called that function. Whereas every return is the same, there are different kinds of calls. So a call can either be direct or indirect. With a direct call, the source code says exactly what function is being called. So in this example here on that side, we have two functions, f and g, and f calls g. This is a direct call because we can look at the source code for f and we can see that it's calling g. When this gets compiled, the call gets baked into the machine code. So for example, on x86, we might have a call g instruction like this. In order for an attacker to hijack control flow on a direct call, the attacker would have to modify the machine code in our program. But the executable code is generally stored in a region of memory that is protected as non-writable, so the attacker can't do that. So direct calls cannot be hijacked. With an indirect call, the source code does not specify a specific target for the call, though. Rather, there's a layer of indirection between the caller and the callee. The basic mechanism for indirection here is a function pointer. And so, for example, in this example, we have a function pointer named GP, and f calls the function pointed to by this function pointer. A function pointer may be located in memory that's writable, right? It might be in a global variable or a struct or class on the heap somewhere, or maybe on the stack. If a function pointer is located in writable memory, then it's potentially possible for an attacker to tamper with it, replacing it with a pointer of their choosing. If the attacker can then get the program to call through that function pointer, then the attacker can hijack control flow. With return address corruption, we saw how an attacker might find gadgets, each ending in a ret instruction, and then chain these gadgets together using return-oriented programming to achieve arbitrary code execution. There's a similar pattern that can be used with function pointers called jump-oriented programming, or JOP, where an attacker takes gadgets that end in indirect branch or call instructions, and then they chain these together in the same way to achieve arbitrary code execution. So the answer to our question is yes, we are going to need technologies to help defend against forward edge control flow attacks as well. So this will bring us to our final definition of what control flow integrity is. Even if an attacker can exploit arbitrary read and write vulnerabilities, and thus can read any byte from the address space of our process, and can modify or corrupt any byte in the address space, we want to prevent the attacker from successfully hijacking control flow. And as before, we assume that the attacker can't change memory permissions. So effectively, our earlier definitions of control flow integrity focus solely on return addresses, but now we'll assume that the attacker can corrupt any state, including return addresses, but also including function pointers, v-pointers, and whatever else. So we already solved this problem for return addresses, so that's good. So now we'll look at the solutions that have been developed for function pointers. Production-grade technologies here are fairly recent, relatively speaking. All of them have been introduced within the last 12 years or so. I'm going to introduce two pure software-based protective technologies, Microsoft's Control Flow Guard and Clang Control Flow Integrity, and then we'll look at a couple of hardware-assisted protective technologies. Before we jump in, though, I want to very quickly note that everything I'm about to say about function pointers also applies to polymorphic C++ classes and virtual functions. I'm going to focus on function pointers because they're simpler to talk about, but just know that both the problems and solutions that we're going to look at apply for virtual functions as well, because like with virtual functions, you basically just have a v-pointer that's a pointer to a table of function pointers. All right, so the first technology that we're going to look at here is Microsoft's Control Flow Guard, or CFG, which was first released in 2014. To start, we'll consider a very simple question. What values can a function pointer have? On a 64-bit platform, a function pointer is just an 8-byte number, so it can have basically any value that can be represented in 8 bytes. But for our purposes, we can group the possible values into two broad categories. Either a function pointer points to a function, or it doesn't. Now, there's a lot of possible values in that second category, right? It might be a null pointer or an invalid address that'll fail address translation, or maybe it points to data or it points into the middle of a function. Who knows? The only important thing is that it doesn't point at a function. So our function pointer may point at a function or it may not. So for control flow integrity purposes, we can start then by saying that it's only valid to call through a function pointer if it points to a function. I know that seems obvious, but that's an important observation. Like there's trillions of bytes in our address space, but there's probably at most only a few million functions. And it turns out we can refine that even further. We can actually say it's only valid to call through a function pointer if it points to a function whose address is taken somewhere in the program. If we have a function and we only ever call it directly, and we never take its address anywhere in the program, then that means we never form a function pointer to it. And boy, at runtime, we should never be calling that function indirectly. So this leads us to the basic principle of Microsoft's Control Flow Guard. Before we make an indirect call, we will check where that function pointer points. If the function pointer points to an address-taken function, then we make the call. Everything works as it's supposed to. If the function pointer points anywhere else, we terminate the program. So here on the left-hand side, I have a function f, and it takes a function pointer fp, and it calls it. With Control Flow Guard, the compiler instruments this call to perform this check. It checks, does this pointer point to a valid call target, an address-taken function? And if it does, it makes the call. And if it does not, then it terminates the program. So this is simple enough. It just leaves us with the challenge of implementing this isValidCallTarget function. So the first thing we have to do is identify all of the valid call targets. So we start in the source code where somewhere we take the address of a function f. The compiler will see this, and it'll put metadata in its object file that says f is a valid indirect call target. The linker will take this metadata from all the object files that it gets, and it'll merge it all into one big list for the whole executable. Then at runtime, the loader is going to load all of the binaries, the exe and the DLLs, and it's going to read this metadata from all of them and merge it into one big lookup table. So yeah, we'll just create one big lookup table. So we can write a first conceptual implementation of isValidCallTarget like this. We can imagine having one big lookup table containing one bool for every address. So it needs to have 2 to the 47th elements in it, because that's the size of the user mode address space on x86, 64. If an address is a valid call target, then its value in this lookup table will be true. If it's not, then its value will be false. Then inside of this function, all we have to do is look up the entry for that target address and see if it's true or false. And that conceptually is how control flow guard actually works. Now, all right, there's like maybe some problems with this. Or like there's one big problem that I'm sure people have noticed. The good news is this valid call targets array has one element for every byte in our address space. Each element is a bool, so it takes up 1 byte. So this array takes up 128 terabytes of memory. You see, this is good news, though, because it means it fits perfectly. The bad news is it doesn't leave room for anything else, so maybe that'll be a little problem. So we can make a couple of optimizations to reduce its size. The first obvious optimization that we can make is using a bool is inefficient. We only need 1 bit to represent a true-false state, not a whole byte. So we can actually shrink our table by a factor of 8 by using a bitmap instead of an array of bools. So now the valid call targets array only occupies 16 terabytes of our address space, leaving 112 for the rest of our program, which is probably enough, but like 16 terabytes is still pretty big. To achieve a further reduction in the size of the bitmap, the compiler and the operating system collude together. The compiler ensures that every single address taken function is aligned on a 16-byte boundary. The operating system then only tracks validity for every 16-byte aligned address. This would, in theory, allow us to reduce the size of the table by a further factor of 16. However, it's possible there still exists some legacy code that has valid call targets that aren't 16-byte aligned. So to handle that case, the OS uses 2 bits instead of 1, and we end up with basically 2 bits in our bitmap for every 16 bytes of our address space. So how big is this bitmap? So the user mode address space is 128 terabytes. After our first optimization, where we switched to a bitmap, the table was 16 terabytes in size. And then after our second optimization, where we store 2 bits for every 16 addresses, the table is 2 terabytes. The table actually does take up that much of our address space, but it doesn't take up anywhere near that amount of memory. Note that like in our gigantic 128 terabyte address space, only a very tiny fraction of that space contains any executable code at all. So the vast majority of this table is just zeros. With the way the control flow guard works, it reserves the whole 2 terabytes of address space for the table, so it won't be usable for other purposes. But it only needs to commit the parts of that table that actually contain at least one valid call target. So it only actually needs to allocate memory for a very small part of this table. As an example of this, I used the VMMap tool from sysinternals to visualize the virtual address space for explorer.exe running on my laptop. I sorted the address space regions by size, and by far the largest region was this CFG bitmap. So this is a screenshot from the tool. We can see the size of the bitmap is 2 terabytes, as we expect, but only about 67 megabytes are committed. So the table, this whole feature, control flow guard, uses only 67 megabytes of memory. Additionally, we can see in this screenshot that that region is shareable. So as an additional optimization, the operating system will share parts of this bitmap across multiple processes in the system wherever possible. For example, there's this one DLL, NTDLL, which gets loaded in every single process. It's loaded from the same file, it's mapped into the address space of every process in the same way, and it has the same set of valid call targets in every process. So that part of the bitmap is going to be the same in every process. So the OS can like share the memory used by that, right? It doesn't need to have a separate copy of that for each process. So that's control flow guard in a nutshell. Control flow guard restricts indirect calls so that they can only be made to address taken functions. The protection here is what is called coarse-grained protection, because any address taken function is potentially callable through any function pointer. That might sound a bit weak. After all, an attacker could overwrite a function pointer with the address of any other address taken function. And there are probably a lot of those. But this does defend against jump-oriented programming, where an attacker might try to call into the middle of a function or into a gadget, and that in itself is pretty substantial protection. It's definitely a huge improvement in security over not having any protection at all. So with that, we'll set control flow guard aside for a moment and look at another CFI technology, Clang CFI. And then once we've looked at that, we'll compare and contrast the two approaches to understand the design trade-offs. So Clang control flow integrity, or Clang CFI, is an umbrella term that for a set of compiler-based security technologies that are all related to control flow integrity in Clang. There's a number of really cool technologies there. I am only going to focus on the indirect call protection because that's what we're talking about in this talk. You should definitely go and check out the documentation for the other cool things that it has. So Clang CFI provides forward edge control flow integrity that has the same sort of protection, the same sort of conceptual idea as Microsoft's control flow guard. With Clang CFI, at each place in the code where we make an indirect call, the compiler will insert instrumentation that checks, does this function pointer point to a valid indirect call target? If the answer is yes, then the call is made. If the answer is no, then the program is terminated. That is where the similarities end, though. Clang CFI is implemented in a completely different way. When we looked at control flow guard, we saw that a function is a valid indirect call target if and only if its address is taken somewhere in the program. The same is true with Clang CFI. However, Clang does something very interesting here. Here on the left, I have a small example. We declare a function g, and then inside of our function, we take the address of g and assign it to a function pointer. So g is address taken. When we enable Clang CFI, the compiler transforms this code into the code here on the right. Clang creates a thunk for g, which for example purposes I have named gthunk, though in reality it has some much more unwieldy name that the compiler likes. This thunk consists of a single instruction that just jumps to the start of g. Then inside of f, when we take the address of g, instead of giving us the actual address of g, Clang gives us the address of gthunk. Clang will perform this transformation every time we take the address of a function, which means the only function pointers we ever have in our program point to these compiler-generated thunks. And this gives us something quite useful. During compilation, we're going to end up with all these thunks. I'm not very creative with my function naming, but for example, if we have functions A, B, C, and D, and all of them are address taken, we'll end up with these 4 thunks here. Each of these thunks consists of a single jump instruction. The jump instruction happens to be 5 bytes in length. And that's actually a very interesting thing, because in general, a function can be any arbitrary length, right? Like maybe A does nothing, and it consists solely of a ret instruction, so it's 1 byte. And maybe B is some gigantic algorithm, and it occupies megabytes of memory. The point is, we don't know. But every one of these thunks is exactly 5 bytes in length. That means that every one of these thunks is exactly the same size. And if we have some things in memory, and they're all exactly the same size, and if we line them all up in memory, one after the next, we can effectively form an array out of them. So here, I've taken our 5-byte thunks. I've added 3 bytes of padding to each so that each element is 8 bytes, because powers of 2 are always nice. I like powers of 2 almost as much as the CPU does. And then I've lined them up in memory so that they form an array. The compiler people will call this a jump table, but we can call it an array if we want. And we give this array a name. I've called it valid call targets, because that's the name we used before, and I like consistency. If we recap what we have here, the only address-taken functions in our program are now these thunks. These thunks are thus the only valid indirect call targets in our program. We've just lined up all these thunks in memory into an array. When we make an indirect call through a function pointer, we want to know, does this function pointer point to a valid indirect call target? Now that we have this array of thunks, this question is the same as, does this function pointer point to an element in this array of thunks? If it does, then it's a valid call target. If it doesn't, then it's not. So we can then easily re-implement our isValid call target function for Clang CFI. We have our valid call targets array, which is our array of thunks. We need to check 2 things. 1, does the function pointer point somewhere within the bounds of the array? So is it greater than or equal to the start of the array and then less than the end of the array? And 2, if so, does the function pointer point to an element in the array and not some random byte inside of that element? And that's it. As I've written the code here, this is 3 conditional tests, which is kind of a lot, but in fact, this can be transformed into a very efficient single conditional test and branch. If you're interested in how to do that, I encourage you to try Clang CFI out and take a look at the code it generates. It's quite clever. Now, a cool thing about the Clang CFI design is that it doesn't require any help from the OS. There's no global bitmap of valid call targets that has to be maintained. The compiler builds up the list of valid call targets itself, and it produces this array of thunks. This design is also cool because it enables us to refine our validity check. Imagine that we have a program, and we have all these functions in it. All of them have their addresses taken somewhere, so they're all valid call targets. However, at a C++ language level, they are not all valid call targets for every indirect call site. When we make an indirect call through a function pointer, that function pointer has a type, and that type must match the type of the function being called. The compiler does its best to enforce this through the type checking. You got to use a cast in order to cast from one function pointer type to another. But even if you do put in one of those dangerous-looking casts, you're still not allowed to call a function indirectly through a function pointer of the wrong type. It's not allowed. The behavior is undefined. So for example, if we have fp1, which is a pointer to a function with no parameters, when we ask, does it point to a valid call target? Ideally, we only want the answer to be yes if it points to A or B, because those have the same type. Similarly, if we have fp2, which has a different type, ideally, the only valid call target should be C, D, and E, because those have the same type. With control flow guard, where we used a bitmap to determine whether an address was a valid indirect call target, we were effectively limited to 1 bit of information for each address. It either is or it isn't a valid target. And we said that was a coarse-grained check. But with Clang CFI, where we're using an array of thunks, we have more flexibility. And that flexibility allows for much finer-grained call target validity checking. Instead of having 1 big array with all of our thunks in it, we can have 1 array for each function type. So if we have these 7 functions, we'd have 1 array with the thunks for A and B in it, and a second array with the thunks for C, D, and E in it, and then a third array with the other 2 functions. And then at each call site, the compiler will say, okay, this function pointer is a pointer to a function that takes 1 int parameter, so I'll perform the validity check using that array of thunks. So at no additional cost, this substantially improves security because it substantially reduces the set of valid call targets for each particular indirect call site. So that is Clang CFI's indirect call checking in a nutshell. Now that we've looked at both of them, we can compare their designs and see what trade-offs were made. The first thing we should, of course, consider is the protection they offer. After all, these are first and foremost features for improving the security of our software. Both of them protect against jump-oriented programming and gadget-style attacks, where an attacker might corrupt a function pointer with the address of some gadget in memory. They're different, though, in how much they restrict an attacker. Control flow guard only has coarse-grained validity checking, so an attacker can, in theory, overwrite a function pointer with the address only of some other address-taken function in the program. Clang CFI has finer grain checking, so an attacker is more limited. If the attacker is going to overwrite a function pointer, they're going to have to pick another address-taken function of the same type. While both technologies offer substantial protection here, Clang CFI is clearly better because the set of valid call targets for each indirect call site is substantially smaller. Control flow guard requires cooperation between the toolchain and the operating system. Clang CFI, on the other hand, is completely toolchain based. It doesn't require help from the OS at runtime. I'm sure you can all imagine why OS independence is of great value to the people working on Clang, and maybe it's of somewhat less value to the people working on Visual C++ and Windows. Control flow guard works with basically any build. You can even enable it for debug builds, and the toolchain will produce the appropriate metadata. When we looked at Clang CFI, on the other hand, and I said the compiler produces this array of thunks, I skipped over a tiny little thing here. In ordinary C++ compilation, where the compiler only sees 1 source file at a time, no instance of the compiler actually knows the full set of thunks, or how many of them there will be. Only the linker knows that when it sees all the inputs to the binary at the end. Thus, Clang CFI requires that we enable link time optimization so that when the optimizer runs at link time, it sees everything. It can produce that array. Now, we should, of course, be using link time optimization. It's awesome. It makes our programs faster. But if we aren't, then we have to enable it if we want to use Clang CFI. And it does mean we can't use it in debug builds, and it does mean that debugging failures can be a little tricky. Control Flow Guard has this neat feature that it's incrementally adoptable. If you have a large application, you can gradually enable Control Flow Guard for parts of it and work over time to get it turned on for everything. It has support for backwards compatibility with old libraries and DLLs that weren't built with CFG. Now, obviously, in that case, its protections are weakened, but partial protection is better than no protection. With Clang CFI, you basically have to enable it for everything in your binary all together, all at once, because that array of thunks must be complete. So there's no easy transition option where you can enable CFI checks for some of your code and not for other parts of your code. There's like an asterisk on that because it does support a blacklist or exclusion list so that you can exclude certain files or functions or types from having CFI checks added, but this can be a bit tedious to fine-tune and get the right things. With Control Flow Guard, indirect calls to dynamically loaded DLLs are easy. The bitmap used to represent validity is global for the whole process, so the information for all the DLLs just gets merged into this one big table, and so checking of cross-DLL calls just works. This is extremely important on Windows, where it is very common to make indirect calls to dynamically loaded DLLs, especially because of the way COM works. With Clang CFI, though, our array of thunks is specific to our one binary. So if we're going to make a call to a function in a different binary that we've dynamically loaded, we're going to have some special way to handle that. And Clang CFI has a few options here, but they all impose an extra runtime cost or reduced protection. Control Flow Guard can work with any language and toolchain. So for example, if you build a new DLL using Rust, and you want to make sure calls between your mostly C++ program and your Rust DLL are checked, that can be done. Microsoft implemented support for Control Flow Guard in LLVM, and it is supported for both C and C++ code and for Rust. Other languages, even JIT compilers at runtime, can provide the required information to the OS about valid call targets. So generally, interop is quite straightforward. Clang CFI is Clang specific and C++ and C specific, so there's no real interop story there. Now, you might ask why you'd need this sort of protection for Rust code, which is safe. And the answer is, well, first and foremost, to protect it from the potentially vulnerable, unsafe C++ code in the process. Because Rust is only safe at the language level. Once it's running on the machine, it's not safe. If you corrupt its runtime state, it's not safe anymore. Finally, the coarse-grained checking that Control Flow Guard does generally just works. The fine-grained checking that Clang CFI does should just work, as long as you're not doing anything funny, like casting function pointers. Unfortunately, it turns out there is an awful lot of code out there that does funny things with function pointers. So depending on your particular code base and dependencies, it can be a bit of a chore to adopt. I've adopted Clang CFI for a very large code base with a lot of dependencies, and it was very interesting to look at the commit history of some of those dependencies and see Google especially making changes to fix bugs there. So my point with this comparison is not to declare a winner or say that one is better than the other. If we look at solely at the protection provided, we can see that Clang CFI is clearly better. But as with almost everything, there's trade-offs. There's pros and cons to the approaches, and it's just interesting to see what might have led to the different design choices here. All right, we're getting really close to the end of the talk, I promise. Microsoft Control Flow Guard and Clang CFI are both pure software defenses. They work on existing hardware and don't really depend on any hardware-specific features to work. I imagine we were looking at 64-bit x86, but nothing that we talked about was x86 specific. Pure software techniques are really nice because they work on existing hardware. And adding new features to hardware is expensive, and there's a very, very long lead time between when new features are added to hardware and then when they're widely usable. But pure software techniques here will tend to have a higher performance impact, right? So for both Control Flow Guard and Clang CFI, we saw that the compiler needs to generate additional instructions to perform the validity check. The CPU is going to have to execute those instructions, and that execution isn't free. So what if we could get the CPU to help us out here? Intel and ARM have both added instruction set extensions that provide hardware support for coarse-grained forward-edge CFI, similar to what Control Flow Guard offers. Intel's implementation is called IBT, or Indirect Branch Tracking. It's part of CET, which we talked about earlier. IBT was introduced in Tiger Lake in 2020. To the best of my knowledge, AMD has not implemented IBT in their chips. I haven't looked in weeks, but I'm pretty sure it's not there. ARM's implementation is called BTI, or Branch Target Identifier. It was added in ARM v 8.5 in 2019, with CPUs coming out a little bit later. So we'll look at Intel Indirect Branch Tracking. It's very simple. It adds a new instruction called end branch. There are two versions of it, endbr32 and endbr64 for 32-bit and 64-bit code, respectively. These instructions are designed to be put at the top of functions. When IBT is not enabled for a program, end branch is a no-op. Old CPUs will also treat the instruction as a no-op, so it's backward compatible. When IBT is enabled for a program, end branch actually is also a no-op. Like I said, it's very simple. What could be simpler than doing nothing? But okay, IBT must be doing something somewhere else. So when IBT is enabled, it's the call and jump instructions that are modified. With IBT, whenever a program makes an indirect call or jump, the next instruction executed must be an end branch. So the idea here is the compiler will put these end branch instructions at the top of every indirectly callable function. When the CPU executes an indirect call, it'll check, boy, is the instruction that's pointed to there an end branch instruction. If it is, then the CPU allows the call and execution continues. If it isn't, then the CPU raises an exception and our program can be terminated. So effectively, we can get something very similar to the coarse-grained protection offered by Control Flow Guard, but implemented in hardware without having to perform the checks in software or maintain this bitmap, so it should be more efficient. ARM's Branch Target Identifier, or BTI feature, is effectively the same, except for a few details. Instead of end branch, the instruction is named BTI, and instead of call, it's a BLR instruction, and then there's just all the little architectural differences. So yeah, hardware support for coarse-grained protection here is quite straightforward. But we already saw that Clang CFI, with its finer grain protection, offered better security improvements. So it'd be kind of cool if we could get that finer grained protection with help from the hardware to hopefully reduce the runtime cost of those software checks. And for that, we come back and end the talk looking once again at ARM pointer authentication. In the first half of this talk, I feel like pointer authentication was kind of a letdown. It seems super cool. At least, I don't know, to me, applying cryptography for protecting pointer values in memory is pretty cool. But while pointer authentication offered very good protection for protecting return addresses on the stack, its protection was not quite as good as the protection offered by shadow stacks, and so it kind of feels a little over-engineered and overcomplicated for that task. But there's one neat thing. It can be used to protect any pointer, not just return addresses. So if we look back at our diagram of how pointer authentication works, and we think about how this might be usable to protect function pointers. So first we have our three inputs, our pointer, which was a return address, but in this case it'll be the function pointer. We have the cryptographic key, which will be provisioned by the operating system for us to use. There's no difference there. And then we have the 64-bit modifier, which we'll come back to. So we feed these three inputs into the pack instruction, and it gives us a signed function pointer, and we can safely write that signed function pointer to memory. Then later, when we want to use that signed function pointer to make a call through it, we'll read it back from memory, and then we'll feed it along with the same cryptographic key and the same modifier into the authentication instruction. And it'll authenticate the signature and either give us back our original pointer, which we can successfully call through, or a tainted pointer, which will cause an exception to be raised when we try to call through it. So if we ignore the modifier, we could pretty easily imagine using pointer authentication to implement coarse-grained indirect call validity checking. Whenever we write a function pointer to memory, we'll sign it first, and then whenever we read a function pointer back from memory to make a call, we'll authenticate the signature. The modifier in this case can just be 0 or some other constant value. If we do this, then an attacker would be able to overwrite a signed function pointer with another validly signed function pointer, but only with another validly signed function pointer. As our program executes, hopefully it's only going to be signing function pointers that point to valid indirect call targets. And since an attacker can only overwrite a signed function pointer with another signed function pointer, that means that an attacker can only redirect a call to another valid indirect call target. So thus, from a security perspective, we get something similar to what we had with control flow guard and indirect branch tracking. But we have this modifier, which can be an arbitrary 64-bit value. The only rule is it must be the same value during both signing and authentication. So if we sign a function pointer when we first take the address of a function, and we authenticate the signature when we're going to make a call through the function pointer, one thing that we know from when we talked about Clang CFI, one thing that we know must be the same at both of those points in time is the type. The type of the function must match the type of the function pointer through which it's called. So what we can do is use the type as the modifier. Now, obviously, we need some way to represent arbitrary function types as integers, and one approach that's been taken here is to hash the function type and use a 64-bit hash code as the modifier. And with that one little trick, we get fine-grained, type-based protection like with what Clang CFI provides. So there's some pros and cons to this approach. On the pro side, well, it's implemented in hardware. It also works across shared library boundaries like control flow guard. But it requires rebuilding every single piece of code to use PAC because function pointers can be passed across those shared library boundaries, and both sides of that interface had better agree on whether those function pointers are signed or not. But if all of your code is built with PAC enabled, this technique is really cool. We get fine-grained forward edge control flow integrity with hardware support that should make it much more efficient than software-based solutions like Clang CFI. So there's been a lot of research here. As of today, I believe the only major platform where this technique is in use is on Apple's platforms. Apple has been working on this for some time. As I mentioned in the first half of the talk, pointer authentication was first added in the Apple A12 CPU, which shipped all the way back in 2018. I believe Apple has had pointer authentication enabled for their system software for a while. There's been a bunch of articles about weaknesses that people have found and then improvements that have been made to it. But it was only this year, just a couple of months ago, that they made it available for you to use in iOS and on macOS 26. So there's a new ABI that you can target when building your application called ARM64E. I think the E stands for enhanced. And so, yeah, there's probably a few people in here with iPhones, so there's probably a lot of pointers being signed and authenticated in this room right now. And with that, we've reached the end of the talk. I hope that you found this an interesting tour of some of the modern technologies being used today to defend against control flow hijacking. I hope there was something new here for everybody. I would be surprised if anyone here knew all of that, because even I didn't know all of that. I had to do a lot of research. I know I covered a lot of material, so a lot of it was necessarily high level and conceptual. There is detailed information online about all of these technologies, documentation, technical talks, articles, academic papers. So yeah, with that, I was hoping to take the full 2 hours so that I would escape the ordeal of taking questions. But alas, I am now happy to answer any questions you may have. If anyone's still awake.
Well, first, thank you for the keynote. So 1 year ago, I had a 5-minute conversation with you before the closing keynote, and that basically spawned this keynote, and you really delivered. Thank you. I have a question from Honey. Amidst increasing software security challenges, what do you think as the main types of mindset changes and fundamental knowledge security guidelines every software programmer should be aware of?
I think the most important thing is to accept that we're going to have security bugs. Like a lot of people, I feel like there's a lot of talk like, oh, if we just use good enough tools, we won't have these bugs. If we just add these new libraries to C++. If we just use C++ correctly, then like we won't have security bugs, or we won't have memory safety bugs, for example. And that's like just false. I will say, like, in recent years, I've probably seen more memory safety bugs involving incorrect use of string view, which is a pretty new library thing designed to help improve like memory safety, than like almost any other category. So like even the new things can be used incorrectly. For us as C++ programmers, like fundamentally, we need to accept that it is an unsafe language, and so we really do need defense in depth, and we need to, from the beginning have secure design, have good coding practices. We need to be using all of our best, static analysis and dynamic analysis tooling that we have. And then, for active protections like control flow integrity, we need to understand our threat models, like what the risks are for our particular applications, and then like which of these technologies are of value. So hopefully that gave some answer to the question.
Hey, it's all pretty cool tech, right? Just a bit sad that it has to exist. So how much time would it take to get into the finicky part of the Clang ICF shared library support?
More than we have here in question and answer.
Okay, thanks.
Yeah. It's fairly well documented. Well, it's documented. Yeah, it's yeah.
So let's say we now go home energized and we enable all these checks and we use all these features and we nail shut the backward edge and we nail shut the forward edge. What further attack vectors, very briefly, should we be aware of that are still open?
Yeah, so I would say the biggest next area are pure data attacks. Right, so all of these are defenses against control flow attacks, where the attacker tries to manipulate the control flow of the program. If the attacker can't do that, then they will try to find ways to change the behavior of the program by changing the data that it's operating on. Right, so by corrupting, state such that the program is executing the code that you wrote that got built into the binary, but it's now doing something potentially different than what was intended. Now, the reason that control flow attacks have been preferred, for a long time, is that they're simpler, basically. So attacking return addresses was the simplest thing to do. So no one was really focusing on jump-oriented programming attacks, because those were really hard compared to just overrunning a stack buffer. So gradually, as we adopt these technologies, attackers will move to harder and harder attack vectors, and I would say pure data attacks are going to, become more prominent probably there.
Well, sold us online. Is C++ safe?
No.
Hi, thanks for the talk. In industrial systems, we do not have the luxury being protected by the ecosystems of Google, Apple, Microsoft. And one could say, yeah, in an industrial product, you can protect yourself. You don't need to be connected to the internet. But with the dawn of the smart home and Internet of Things, we connect even more electronics to the internet, and those will be at some point attacked as well. Those are mostly ARM processors. What would you suggest as the baseline? What of these techniques that you've shown would you recommend as a baseline for such systems?
Okay, so I'm first just going to say I know almost nothing about anything smaller than the cell phone. So I'm going to just guess here. Some of these are just fairly basic technologies that should be available on general ARM chips, right? If you support virtual memory, then having non-executable allocations should be a thing that you should be turning on. I would say that unless you're in an extremely resource-constrained environment, shadow stacks, once they're available on ARM chips, should be a thing that you would be able to turn on in that environment. If not, then definitely you want to continue using stack canaries. On larger systems, once you have shadow stacks, you don't need stack canaries at all because they are completely redundant. So both of those are important. For the forward edge protection, if you're on ARM, then having the BTI, the branch target identification, is an option. Linux supports it, I think. If not, then support is in the works. And of course, if you're using some embedded real-time operating system, you do need support for almost all of these from at least a little support for almost all of these from the operating system. So there, you'd get into embedded systems domain stuff that I can't answer because I just don't have any experience there.
So what's your own experience like with these technologies? As one of the things which I found interesting is that you work with these things.
Yes. So I was a member of the Visual C++ team at Microsoft while Control Flow Guard was being developed. I did not actually work on it, but the people who did were a few offices down the hall, so I was very familiar with a lot of the work that went into it. There were tremendous challenges to make it fast enough to turn on. So that's that one. I have personally used Clang CFI on numerous systems, so I'm very familiar with that. In my last few years at Microsoft, I worked on basically the design, the plans to use pointer authentication for protecting return addresses for Windows on ARM. As I said when I talked about that, I actually don't know what the state of that is at this point in time because the compiler option isn't in the documentation, so they may have chosen to go a different route. But yes, so I've got some personal direct experience with most of these technologies.
Thanks for the talk, very insightful. I have a question regarding overhead. Do you know any of these techniques, what overhead they have? And yeah, let's start with this.
It's a great question. I am so surprised that at a C++ talk someone asked about performance. I actually didn't really talk about performance intentionally. And the answer is, for some of these technologies, the performance overhead is so negligible it doesn't matter, right? So for example, having non-executable memory is basically free. Similarly, shadow stacks, yes, you've got this extra stack for the program, but since all of the behavior is just they're tweaking the behavior of the call and ret instructions, it should be extraordinarily low runtime overhead. And then even the memory overhead is fairly low because while the thread stack, may be megabytes in size, the control flow stack only contains return addresses. So you can fit 512 frames on every page. So generally, it's only going to be 1 or 2 pages, in size. So the memory overhead's very low. The runtime overhead's very low. For the forward edge protections, Clang CFI and Control Flow Guard, there is an overhead. Every indirect call becomes more expensive. What that overhead means for your application depends entirely on what your application is. If you don't make a lot of indirect calls, you'll never notice the overhead. If you could imagine writing a worst case thing where you've just got a giant array of 1 billion function pointers and they all point to different functions and each function just returns and you just loop over them and start calling them. I mean, that's absolutely the worst case, right? Because it's going to have tons of overhead. So really, it just depends. For pointer authentication, the instructions do cryptography, so they do take I think the numbers were 3 to 5 cycles, something in there, of latency for these signing and authentication instructions. But they're designed in such a way that basically at the beginning of your function, it starts signing, and then the CPU is off doing that while it's executing your function. And at the end, it starts authenticating, but it can speculate the return, and it can just start executing. And of course, speculation is always scary for the security people. But in this case, it's only ever going to speculate wrong once, right? Because if it speculates wrong, that means that authentication failed, and it's going to terminate the program. So it's not really a big deal. So I guess the big thing is you just you'd have to measure it for the particular application. But all of these technologies are, at this point, in widespread use on major platforms, including in performance-critical environments. So I'm sure that there are devices in this room, laptops and other things that are using every one of these.
Okay, and then linked question. So is it possible to disable everything of this?
Is it possible? Yeah. Oh, yeah, you can disable all of these things.
Even on the operation system level?
Yes, I mean even like address-based layout randomization. Like I don't know about every OS, but Windows has a whole list of mitigations that you can just set flags for a particular process. You have to have sufficient privileges to do that, but yeah, you can disable all of these.
Okay, thank you.
Well, follow-up question from Hani. Could you just suggest any references, talks, courses, books for software security fundamentals for non-cybersecurity programmers and folks?
I will have to think about that. I do not have anything off the top of my head that I would suggest. The one challenge I would have there, like most of the things that I would think of are very targeted, like niche, like here's details on like this feature or this thing or this, and they're not broad like overviews on software security. And then of course, which of those like niche subjects you'd be interested in, like everyone's going to have their own preferences there. But I'll try and think and see if I can think of anything there.
So the examples that you've shown have seemed to like they actually consist of two components. You have a function that is not you use something from the language like the gets or something that is you are not properly constricting towards it's supposed to do. But the one thing I feel like I would want to ask about is that the other component that you actually need some sort of interface as well for the attacker to do this sort of injections. It's not just a memory safety issue, it's also that we have this interface that they can inject things in. So I was wondering, like you talked about the terminal input, about network input, reading about files. Are there other similar attack vectors that might not be so obvious that we as developers should be aware of?
Yes, so certainly like any sort of data that gets written to a file, passed over the network, passed like through a syscall between like user mode and the kernel, or even like vice versa, depending on like where the privilege boundaries are there. Any sort of case where you have like inter-process communication, any sort of remote procedure call, like basically it's important to understand like in your application what the privilege domains are, like which might be a process, it might be a machine, it might be whatever it is, and then understand all of the different like paths that data follows between those. And any path where data is transferred from one privilege domain to another is potentially a place where like an attacker can interact with from one system from one privilege domain to another.
Thank you.
Online question. Guillaume asks, many companies don't care about security, that's true, until it's too late, often leading to catastrophic consequences, losing clients, losing market credibility, etc. Do you think us as developers have some responsibility to prevent it upfront beyond safety and safety and
I think that at a bare minimum, we developers have a responsibility to advocate for good development practices and good security practices. I think that there's a spectrum there between like, oh, we are like die-hard focused on security, and then like at the other end there's like we don't care about security, like, and you just completely ignore it. Or like there was a question, can we turn off these things? Like, oh, we turn off the security features, we're not interested in those. But then like in there's a spectrum of things, right? Like maybe okay, we turn on some of the features, we use some of the tools, but we're not turning on everything, we're not using everything, and it becomes hopefully it becomes a gradual thing where you ratchet your way, toward we actually care deeply about security. So, like, I don't think that developers have a responsibility to, like, just start, saying, oh, we have to stop everything and immediately focus on security only and go and, like, solve every problem. I do think that, like, we absolutely have responsibility, though, to go and advocate for best practices. And, that doesn't necessarily mean adopting them in entirety all at once, but it does mean like improving whatever the status quo is and like gradually making improvements. So kind of like at the beginning of the talk, I said, we're going to have memory safety bugs, right? And so just like that, like we have to accept that and figure out what we're going to do with it. Similarly, like, hey, you know what? If your organization is in a bad state with respect to security, the most important thing you can do is accept that and like be honest about it, and then try and find the most cost-effective ways to improve things, even if they're only small improvements, because the small steps will add up.
Thank you for the talk. You mentioned call protection on Windows in Clang. Is there something for GCC?
I do not. So I'm not particularly familiar with GCC. I don't use it. And I could not find information about something similar. So the technology that is used now for Clang CFI, when it was originally developed in Clang and GCC. Like, I don't know if in parallel or if they were different teams, but they were like the early papers on it like are in both compilers. But there's no I could not find compiler options to turn this on in GCC.
Thanks.
I will give a caveat. Some of the other technologies are there. So, for example, enabling shadow stack support for your binary or pointer authentication. There are options for some of those things. I know there's been a lot of work because like the Linux kernel and Linux core like teams are really interested in that. But for Clang CFI specifically, I don't believe there's an equivalent technology in GCC.
I wonder what about GPUs, as these are also becoming, important.
It's a great question. I do not know the first thing about GPU programming, and so I would not want to speculate.
Yeah, I think. Thank you.
All right. Thank you.
Thank you.